Welcome to a special case. So let's consider differential equations. Of the form uh, 1 plus alpha times x minus x naught, the x minus x naught being squared, times y double prime plus beta times x minus x naught times y prime plus gamma times y equaling 0. Here where alpha, beta, and gamma are in the real numbers. Quite a few famous differential equations take this form. Including Legendre's equation, I need to give myself a little more space. So including Legendre's equation, which takes the form 1 minus x squared times y double prime minus 2xy prime plus alpha times alpha plus 1 times y equals 0. So in this case, what previously was acting as our x naught is 0. What previously was alpha is -1. Our beta is -2. And our gamma is this alpha times alpha plus 1 that we see here. So this is in the special case. Lagrange's equation has applications in electrostatics. So this has applications in electrostatics and electromagnetic wave propagation. As well as single particle quantum mechanics. There are quite a few other named differential equations that do take this special case, but I'm not going to go ahead and run through all of them. So let's go ahead and look at the general solution to this special case. So we have 1 plus alpha times x minus x naught in parentheses squared, all of that times y double prime plus beta times x minus x naught times y prime plus gamma y is equal to 0. So again, we're going to go ahead and assume that our solution is a power series in x minus x naught. So let's assume that y equals the sum from n equals 0 to infinity of a sub n times x minus x naught to the n is a solution. Then we have y prime is the sum from n equals 1 to infinity of n times a sub n times x minus x naught raised to the n. And y double prime is the sum from n equals 2 to infinity of n times n minus 1. I apologize, I keep doing the n. This should have been to the n minus 1 for the first derivative. For the second derivative, we should have the sum from n equals 2 to infinity of n times n minus 1 times a sub n times x minus x naught to the n minus 2. Power rule, we're just dropping that power by 1, multiplying by the previous power. So plugging this into the equation, we have 1 plus alpha times x minus x naught squared times that second derivative, so times the sum from n equals 2 to infinity of n times n minus 1 a sub n x minus x naught raised to the n minus 2. Then we have plus beta times x minus x naught times that first derivative, so times the sum from n equals 1 to infinity of n times a sub n times x minus x naught raised to the n minus 1 plus gamma times the original solution, so the sum from n equals 0 to infinity of a sub n times x minus x naught all raised to the n, and this whole sum should be equal to 0. So first thing you want to do is go ahead and multiply in that each of the things multiplying are various sums. So this first sum, we're going to actually wind up with two sums. We'll multiply by 1 and we'll multiply by the alpha times x minus x naught squared. So multiplying that first one in, we wind up getting just the sum from n equals 2 to infinity of n times n minus 1 times a sub n times x minus x naught to the n minus 2. Multiplying in the next piece, we have plus the sum from n equals 2 to infinity of n times n minus 1 times alpha times a sub n. Actually, I'm going to put the alpha in front of the n's. So you have alpha times n minus 1 times a sub n. Multiplying in x minus x naught squared, we just bring that power back to n. So we get times x minus x naught raised to the n. Then that second row, we multiply in our beta x minus x naught. So our coefficient now becomes, we have the sum from n equals 1 to infinity of beta times n times a sub n. Multiplying in that x minus x naught brings the power up by 1. So we have x minus x naught raised to the nth power. And then multiplying in gamma, we're taking the sum from n equals 0 to infinity of gamma times a sub n times x minus x naught to the n. All of this should equal 0. So note here that we actually only have one term that requires a shift. We have a term that has n minus 2. Let me restart my screen. It's not updating. Again, we have a shift. We have a power of n minus 2 for our nth term. So now we want to go ahead and reset this. We will rename it with a k, where k is equal to n minus 2. So we are going to reindex. So reindexing, we are looking at the sum from k equals 0 to infinity. We're shifting by 2, so this becomes k plus 2 times k plus 1 times a sub k plus 2, all multiplying x minus x naught raised to the k. Then that next one that's hiding behind my video, we are looking at plus the sum from n equals 2 to infinity of alpha times n minus 1 times a sub n times x minus x naught raised to the n. Then we have plus the sum from n equals 1 to infinity of beta times n times a sub n times x minus x naught raised to the n. And then plus the sum from n equals 0 to infinity of gamma times a sub n times x minus x naught raised to the n. All of this again equals 0. At this point, note that for this sum, if n equals 0 or 1, that n times n minus 1 is equal to 0. Similarly, for this one, if n equals 0, then we have again our beta n is equal to 0. So in both of these cases, we can add those missing indices without changing the actual sum. So adding in the missing indices will not change the sums. So I'm going to go ahead and just do that. So we are looking at, and then this one, I'm just going to again swap it out and just say n is equal to k. So rewriting this, we have the sum from n equals 0 to infinity of k plus 2, sorry, of n plus 2 times n plus 1 times a sub n plus 2 times x minus x naught raised to the n, plus the sum from n equals 0 to infinity of alpha times n minus 1 times a sub n times x minus x naught raised to the n, plus the sum from n equals 0 to infinity of beta times n times a sub n times x minus x naught all raised to the n, plus the sum from n equals 0 to infinity of gamma times a sub n times x minus x naught raised to the n. All of this again equaling 0. And now we're going to go ahead and just combine all our sums together. So combining the sums, we wind up getting the sum from n equals 0 to infinity of, we have n plus 2 times n plus 1 times a sub n plus 2. That's our only a sub n plus 2 term. All the other ones are a sub n. So then we have plus alpha times n minus 1 plus beta times n plus gamma, that whole sequence from alpha times n all the way up through gamma, that is multiplying a sub n. And then this entire thing from our n plus 2 times n plus 1 all the way through to the end of that a sub n, this is multiplying our x minus x naught to the n. This should be equal to 0. So matching coefficients, with the right side, zero is just equal to 0 plus 0 times x minus x naught plus 0 times x minus x naught squared, etc. So we get that each of these coefficients, n plus 2 times n plus 1 times a sub n plus 2 plus alpha times n minus 1 plus beta times n plus gamma, all of that multiplying a sub n, that whole piece should be equal to 0. And now if we go ahead and solve for an plus 2, we get that a sub n plus 2 is equal to negative alpha times n minus 1 plus beta n plus gamma divided by n plus 1 times n plus 2. That entire fraction multiplying a sub n. So our general solution so thus we have that equation 1 plus alpha times in parentheses x minus x naught, that whole x minus x naught squared times y double prime plus beta times x minus x naught times y prime plus gamma times y equaling 0 as solution y equals the sum from n equals 0 to infinity of a sub n times x minus x naught raised to the n, where a0 is just the initial condition y of x naught. A1 is the initial condition y prime of x naught if we have initial conditions. So, or unknown if there are no initial conditions. And then a sub n plus 2 is negative alpha times n minus 1 plus beta times n plus gamma, I apologize for the spelling, all over n plus 1 times n plus 2, that whole fraction multiplying a sub n. Note here, the even indices are all related to each other and the odd indices are all related to each other. So the even indices right, a sub 2k can all be written in terms of a0. And the odd indices a sub 2k plus 1 can all be written in terms of a1. So if we have a differential equation that takes this very special form, then we can jump straight to the solution without and just solve sort of based off of the alpha, beta, and gamma that we have, solve for the various coefficients without having to go through all of the other algebra just to get to this point. But the technique that we're using here, matching coefficients, etc., is useful for solving any differential equation that we don't immediately know how to solve or don't know how to solve using other techniques.